So we've studied identities. Now we're going to study equations. Now, let's see if we can note the difference. This is an identity. Sine squared x plus cosine squared equals 1. That's an example of an identity. And what makes an identity is that it's always true. No matter what you choose for x, this is true. Sine squared 15 degrees plus cosine squared 15 degrees is 1. This is always true. This, however, is an equation. This is only true for certain values for x. So we kind of rely on context to know what we're dealing with here. Here, this is an identity, and this is an equation. So this type of problem, if you encounter this, you might be asked, solve for x, or find the values for x where this is true. So how would we do that? How would we solve for x so that, or how would we solve such an equation? Well, this is saying the sine of something equals 1/2. What is that something? What is that x? Well, one of the things you could do is you could, look at the unit circle and see, well, I know that sine is the vertical component, and I see that we have 1/2 here, so that's sine of pi over 6. So sine of pi over 6 is 1/2. And we also note that over here at 5 pi over 6, that's where we have a vertical component of 1/2. So we might say, okay, let's look at what we have here. We have a solution is pi over 6, and then there's another solution, 5 pi over 6. There. So sine of pi over 6 is 1/2, sine of 5 pi over 6 is 1/2. So we've solved this equation. But hold on a minute. Look at this. Let's just consider this solution pi over 6. Notice that, yeah, sine of pi over 6 is 1/2, but what if we go around the circle again? And we get a coterminal angle with pi over 6. In other words, what if I take this pi over 6 and add 2 pi and go a trip around the circle? Well, I'm right back at 1/2. Okay? What if I add another 2 pi? I'm back at 1/2. What about another one? I'm back at 1/2. So we can see that these are not the only two solutions. In fact, coterminal angles with pi over 6, we could add 2 pi and get a coterminal angle. We could add another 2 pi and get another one. We could add another 2 pi, and we could just go on and on and on, adding 2 pi's, addressing the coterminal angles to pi over 6. Or we could just say pi over 6 plus 1 times 2 pi, or plus 2 times 2 pi, or 3 times 2 pi. In fact, we could say, let's just call it pi over 6 plus k times 2 pi, where k is an integer. In other words, here we have 3 of the 2 pi's, but we get a solution for every time we add a 2 pi. So we could say pi over 6 plus k times 2 pi, or it may roll off the tongue a little easier if we say pi over 6 plus 2k pi. That's the way it's often stated. And we could do the same thing over here. We could say 5 pi over 6 plus 2k pi, like that. So the solutions, all the solutions for sine x equals 1/2, all of them can be represented this way. Pi over 6 plus 2k pi, 5 pi over 6 plus 2k pi. Those represent the solutions. Now let's take a look at what this would look like graphically. So here I've graphed sine x and 1/2. So I've got sine x here, and then I graph down here on a new graph y equals 1/2. And what we're really looking for is we're looking for the intersection. So for example, this point right here, notice that's pi over 6. And over here, this would be 5 pi over 6. So we found, those are the two solutions we found, pi over 6 plus, and then there's 5 pi over 6. But also notice that we could go over a little bit. Let's just think about this 5 pi over 6 and the coterminal angles. If we go over here, we get 13 pi over 6. So notice, this and this are coterminal angles. In fact, if you take pi over 6 and add 2 pi to it, you get 13 pi over 6. And you can look at all of these. All of these are coterminal angles with pi over 6. There's 25 pi over 6, and you can just go through here and identify those. And the second, so this is going up to the maximum, and then on the other side of the maximum, you've got those coterminal angles with 5 pi over 6. But that's what it looks like graphically. And in fact, you could solve that equation graphically. We didn't. We used the unit circle, but you could solve it graphically. Now let's look at another one. Let's suppose that instead of sine x equals 1/2, we've got sine 2x equals 1/2. So how is that going to change what happens? Well, the way we proceed with this is, notice we've got sine of something equals 1/2. And it doesn't matter if that's sine x or sine theta, whatever. We need to say, okay, what does 2x need to equal so that sine of that equals 1/2? So in other words, we found from the previous problem that 2x needs to equal, for example, pi over 6 plus 2k pi, where k is an integer. Okay? So notice what I'm doing different is, instead of pi over 6 plus 2k pi, I've got, that's, in other words, instead of x equals pi over 6 plus 2k pi, I've got 2x equals that. But we don't want to know what 2x equals. We want to know what x equals. Well, I've got this part. Now I just go back and divide everything by 2. So I've got pi over 12 plus k pi. See? Changed a little bit. So we just divided everything by 2, and we had 2x equals 5 pi over 6 plus 2k pi. Now I just need to divide everything by 2. So I get x equals 5 pi over 12 plus k pi. So remember, when we have sine 2x, you can think of it as sine goes through its cycle twice as fast as sine x. So it makes a cycle, instead of taking 2 pi, it takes pi. So you can notice that here. You have pi over 12 plus k pi instead of plus 2k pi. So that's how we would deal with something like that. Now, let's look at another one. So we've got 2 sine x minus the square root of 3 equals 0. So we've added some things to this. Well, here's the way we approach this. We, first of all, solve for the sine function. So I'm going to add square root of 3 to both sides and then divide by 2. And what we get is sine x equals the square root of 3 over 2. Okay, now I've got, this is just like the equation we looked at before. We can go back to the unit circle and find where sine is equal to the square root of 3 over 2. Right here. Okay, and that corresponds to pi over 3. And also, we notice over here, corresponding to 2 pi over 3, we've got the square root of 3 over 2. So we got that x is equal to pi over 3 plus 2k pi, where k is an integer. And also, another solution would be 2 pi over 3 plus 2k pi. So there we've got a couple of solutions. Well, this represents all the solutions, 2 angles and then all the coterminal angles. Now, let's look at this. Let's suppose that we've got a situation like this. Tangent squared x equals 1, let's say. So we want to solve something like that. Now notice that, recall, we need to solve for the trig function first. So I need to square root both sides. So I've got tangent x equals plus or minus the square root of 1. So it equals plus or minus 1. Now, we ask ourselves, well, where does tangent equal 1 or negative 1? Well, it equals plus or minus 1 to those angles that correspond to having a 4 on the bottom. For example, pi over 4, 3 pi over 4, 5 pi over 4. What? 5 pi over 4, or 7, and then 7 pi over 4. So when you go one time around the unit circle, you encounter these angles. See? Check this out. Here's pi over 4, where we have this sine over cosine. That's 1. And then over here we have 3 pi over 4. Sine over cosine is negative 1. See? Because the x and the y are either the same or the opposite. That's how you get plus or minus 1. And then 5 pi over 4. See? Sine over cosine. And then 7 pi over 4. Sine over cosine, you get negative 1. Yeah. So here, 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 and here. Now notice that, let's just take notice on, in other words, in every quadrant we have a solution. So we could do this. Let's just write down what the solutions are. We could say this. We could say, okay, I've got a solution at pi over 4 plus 2k pi. And that takes care of all the coterminal angles. And we've also got 3 pi over 4 plus 2k pi. We've got 5 pi over 4 plus 2k pi. And we've also then got 7 pi over 4 plus 2k pi. So we've got these solutions. Now notice that at pi over 4 and at 5 pi over 4, we've got that tangent is positive 1, and at 3 pi over 4 and 7 pi over 4, tangent is negative 1. This is something we can observe here. But something else we can observe. Look at this. Now remember that tangent, it's true that each one of this will give you all the coterminal angles to pi over 4. This one, all the coterminal angles for 5 pi over 4, and so forth. But remember, tangent's period is not 2 pi, it's pi. So I'm thinking that instead of adding a 2k pi, there ought to be something else we would add. Now let's think about this. Let's consider pi over 4, and what if we just add pi to that? Let's see what we would get. Well, pi over 4 plus 4 pi over 4, that's pi, gives you 5 pi over 4, which is that. In other words, what I'm saying is, if we take this pi over 4 and add pi to it, we get the 5 pi over 4. And if we add pi to 5 pi over 4, we get back to a coterminal angle with this pi over 4. So why don't we just do this? Let's just combine these and say, okay, this is pi over 4 plus k pi. Now, if you don't make this observation, that's fine. This is just a more concise way of writing the solution, realizing that tangent's period is pi. But you can combine these. And in the same way, you can combine these two to 3 pi over 4 plus k pi. So there we've represented all of the solutions. Okay, so let's look at one more. Let's suppose that I've got 4 cosine 2x minus 3, and let's make this squared, equals 0. Okay, so this one's got a lot going on with it. Let's suppose we want to solve this one. Well, first of all, we solve for the cosine. So we've got cosine squared of 2x equals 3 over 4. Okay, now we square root it, and we get cosine 2x equals plus or minus the square root of 3 over 2. See? Because the square root of 3, we just write that way, and then the square root of 4 is 2. So we're looking for all of the places where cosine is equal to either plus or minus the square root of 3 over 2. Now, once again, you can go back to the unit circle. Now, remember, cosine is the horizontal component. So here you got pi over 6, that's positive, negative, 5 pi over 6. See, there's a negative square root of 3 over 2. And then you've got 7 pi over 6 and 11 pi over 6. So we could write those solutions. We could say this, okay, I've got 2x equals pi over 6 plus 2k pi. I've got pi over 6, 5 pi over 6 plus 2k pi. Okay. And then I've got, so that's first quadrant, second quadrant. What about the third quadrant? We've got 2x equals 7 pi over 6 plus 2k pi. And then finally, 2x equals 11 pi over 6 plus 2k pi. There we go. So we found, so what we've done is we said, okay, in this situation, I know what 2x equals. But remember, we want what x equals. So this is going to give us, so x is equal to pi over 12 plus k pi. X is equal 7 pi over 12 plus k pi. See, I'm just dividing through by 2. And then over here, I've got, let me move the camera over a bit, x equals 5 pi over 12 plus k pi. And finally, the grand finale, x equals 11 pi over 12 plus k pi. There we have it. So there we have our solutions, all the coterminal angles. All the solutions are represented here. Yeah. So, and now, notice that if you take, as far as combining these, notice that if you take the pi over 6, and if I, going back to this one, if I take pi over 6 and add pi to it, notice you get 7 pi over 6. So if I take pi over 6, and if I add pi to it, I get 7 pi over 6, which is that right there. So maybe, you can play around with these. I could have combined these and said, well, 2x equals pi over 6 plus k pi. I could have gone that route. But anyway, this is how we go about solving these equations.